All right, guys, let's start. So now we are doing your lesson number 3 of chapter number 1. So lesson number 3 of chapter number 1 is Convergence Concepts. And we're still doing your chapter number 1, which is your probability foundation for stochastic calculus. Okay. So the lesson studies convergence. How a sequence of your random variables, stochastic processes, numerical approximations, or your estimator approaches, right? A limiting object. Again, I'll repeat. The lesson studies convergence, basically how a sequence of random variables, stochastic processes, numerical approximations, or estimators approaches the limiting object. This matters because quantitative finance repeatedly replaces something complicated with an approximation. A binomial tree approximates a continuous time stock price model. A discretized stochastic differential equation approximates its exact solution. Monte Carlo average approximates an expected payoff. Sample returns approximates the unknown return distributions. Discrete hedging approximates your continuous hedging. The central question is not simply whether something converges, but in what sense it converges. Different convergence concepts provide different strengths of guarantee. With this introduction, let's deep dive and understand. Now, we'll try to understand the concept of almost sure convergence, right? So, almost sure convergence, strongest notion of convergence, a sequence of random variables converges almost surely when convergence occurs for every outcome except possibly outcomes contained in a probability 0 set. The slide definition is this. The probability of the set of omega belonging to the capital omega such that the limit as n tends to infinity of x sub n of omega equals x of omega is equal to 1. Capital omega is the sample space, the set of all possible outcomes. Lowercase omega is one particular outcome of market scenario. X sub n is the nth random variable in the sequence. X is the limiting random variable, P denotes probability. The expression inside braces is an event, the collection of outcome for which the numerical sequence converges. A sigma algebra, although not shown explicitly, is the collection of events to which probabilities can be assigned. Okay. The equivalent pathwise statement is this. Basically, x sub n of omega tends to x of omega for almost every omega. Right. Now, almost every means it's almost every. Almost every means that any outcome where convergence fails from a null set, a set with probability 0. Almost sure does not mean that failure is logically impossible. Please understand this very clearly. Common confusion, almost every means that any outcomes where convergence fails form a null set, a set with probability 0. Almost sure does not mean that failure is logically impossible. A probability 0 outcome may still belong to the sample space. For sample, an exact point in a continuous distribution has probability 0, but is not an impossible value. Technical clarification here is that calling almost sure convergence the strongest concept is reasonable when comparing it with convergence in probability and convergence in distribution. However, almost sure convergence and convergence in your L, right, to the P are not generally ordered without additional assumptions, right? Financial interpretation here is very, very important is if each omega represents one complete market evolution, almost sure convergence, say that the approximation converges correctly along almost every market path. Okay, so almost sure convergence means convergence hold except on a null set. It is strongest commonly used convergence concept. Why it matters is because many results in stochastic calculus and finance are valid, almost sure ignoring only probability 0 pathologies. Then we get into sample path by sample path convergence. Okay, for one outcome omega, once omega has been fixed, the random variable become ordinary numbers, right? Which is x sub 1 of omega, x sub 2 of omega, and so on. Almost sure convergence examine whether this numerical sequences approach the limit, right? X sub n of omega tends to x of omega. The important idea is that we are not merely comparing the distributions. We are looking at convergence along your individual outcomes. If you look at diagram, right? Diagram explanation, the horizontal axis represents the time running from 0 to 1. The vertical axis represents the value of the process. The thick black curve, the thick one, the thick black curve is labeled as the limiting path. The nearby thinner curves represent successive approximating path. As the approximation is refined, the paths are intended to move closer to the limit path. In finance, an entire stock price trajectory is one path. Almost sure pathwise convergence means that outside and outside increasingly refined approximations towards the correct trajectory. And technical clarification here is for stochastic process, one must specify whether path convergence is pointwise in time or uniform over time. The diagram is conceptual. It does not state which functional convergence metric is being used. Okay. Then we get into the next one, which is financial example approximating Brownian motion. Brownian motion can be understood as the continuous time limit of many small independent shocks. Brownian motion can be understood in the way that random walk increments satisfy this equation. How do you read it? The probability that z sub k equals plus 1 equal the probability that z sub k equals minus 1, and both are equal to 1/2. Here z sub k is the kth random shock. Each shock is either plus 1 or minus 1. The shocks are independent and identically distributed, meaning the distribution is same and are kind of independent. Independence means one shock does not reveal the next shock. Identically distributed means that every shock follows the same probability law. The scaled random walk is this: W sub t superscript n equals 1 divided by the square root of n multiplied by the sum from k equals 1 to the floor of nt of z sub k, where t is greater than or equal to 0 and less than or equal to 1, right? So if you look at the W sub t, right? W sub t superscript n is the n step approximation at time t. The floor of nt is the greatest integer less than or equal to nt. The summation adds all shocks observed up to time t. Dividing by the square root of n prevents the variance from exploding. The number of shock growth. The superscript n identifies the approximation level. It is not an ordinary path, right? The convergence statement is this: W superscript n converges weakly or converges in distribution to W. If W is the standard Brownian motion, this is the process level convergence in distribution in a suitable function space. It does not mean that the original random walk path automatically converges almost surely to Brownian path on the original probability space. The result explains why many small discrete shocks can be modeled by continuous Brownian motion. It underpins binomial to Black-Scholes convergence, Monte Carlo generation of Brownian paths, numerical simulation of GBN has done an interest rate model. The Brownian motion can be used under either the real world or risk neutral measure. What changes between the measure is primarily the drift time interpretation, not the basic Brownian scaling. Okay. So then we get into the next part. The convergence in probability. Convergence probability is the practical weak convergence. Basically, convergence in probability asks whether the probability of a materially large error tends to 0. The definition is given by this formula. The limit as n tends to infinity of the probability that the absolute value of x sub n minus x is greater than epsilon equals 0 for every epsilon greater than 0, right? Here, the absolute difference is the approximation error. Epsilon is any fixed positive tolerance. The event inside the probability is the event that the error exceeds the tolerance. The definition says that this bad event becomes increasingly unlikely. The notation given here is this, which is x sub n converges in probability to x. This does not require convergence along your almost every individual path. It only says that for any chosen tolerance, the probability of being outside the tolerance vanishes. Event versus your random variable also we need to understand. X sub n minus x is a random variable. Its value depends on the outcome. The condition that its absolute value exceeds epsilon describes an event. Probability is assigned to the event, not directly to the random variable. Financial interpretation of financial application include consistency of Monte Carlo estimators. convergence of estimated means, volatility, and correlation, numerical approximation whose probability of large errors becomes negligible. Okay, and then widely used in statistics and Monte Carlo, natural for convergence, for estimators, and approximation. Then we get into the next part, which is comparing your convergence concept relationship between almost surely convergence and convergence in probability. Basically, the main implication is this equation: x sub n converges almost surely to x implies the x sub n converges in probability to x. Why? Because the error converges to 0 along almost every path. The probability of observing an error larger than any fixed tolerance must eventually vanish, right? The reverse implication is generally false, right? So keep that in mind. X sub n converges in probability to x does not imply that x sub n converges almost surely to x. Please understand, convergence in probability permits the exceptional outcomes to change with n. Thus, at every stage, the error may be unlikely, while some individual paths can still experience large errors infinitely often. And if you look at diagram, right? What is diagram doing? The diagram places almost sure convergence on the stronger side and convergence in probability on the weaker side. The arrow only runs from the stronger guarantee to the weaker guarantee. For many pricing applications, convergence in probability is sufficient. A Monte Carlo estimate does not need a guarantee for every realized infinite simulation path. It needs the probability of significant estimation error to become small. Okay, so remember that point. Then we go to slide number 7, which is nothing but quant finance example, Monte Carlo estimators and the LNN. So suppose the target is the expected value, mu equals the expected value of x. Here x may represent the simulated payoff, loss, another financial quantity. Mu is this population mean given independent simulation. The Monte Carlo estimation is given by this. Mu hat sub n equals 1 divided by n multiplied by the sum from k equals 1 to n of x sub k. X sub k is the result from simulation k. Mu hat sub n is a sample average based on n simulation. The hat indicates an estimate rather than the unknown exact value. Strong law of large number, LLN, right, gives us mu hat sub n converges almost surely to the expected value of x. Therefore, mu hat sub n converges in probability to the expected value of x. For risk neutral option pricing, the exact valuation relationship is given by this formula. What is this formula? Basically, V sub 0 equals exponential raised to the power minus RT multiplied with expected value under Q of H. Here, V sub 0 is the option value today, H is the payoff at maturity, R is the continuously compounded risk-free rate, T is the time to maturity, Q is the risk neutral probability measure. The exponential term discount the expected future payoff today. The Monte Carlo approximation on the slide is given to you. Price is approximately equal to exponential raised to the power minus RT multiplied by the mu hat sub n. As the simulation count grows, the estimator stabilizes on the required expectation. The technical clarification here is if x has already been defined as a discounted payoff, it should not be discounted a second time. The displaced pricing formula is appropriate when the simulated x values are undiscounted terminal payoffs generated under the risk neutral measure, right? For forecasting your returns or real world risk, simulations are normally performed under the real world measure, right? Real world measure instead, pricing appropriately and forecasting probabilities have different purposes. Okay. Then we get into next slide, slide number 8. We're talking about convergence, right? And we are looking at mean convergence, right? So the parameter P satisfies P is greater than or equal to 1. A sequence converges in L to the P when we have this equation, the LP norm of x sub n minus x tends to 0 as n tends to infinity. The L to the P norm is defined by this equation. The LP norm of y equals the expected value of the absolute value of y raised to the power P, all raised to the power 1 over P. Then we have this equation, x sub n converges in L to the P to x if and only if the expected value of the absolute value of x sub n minus x raised to the power P tends to 0. This controls the average magnitude of the approximation error, not merely the probability that an error occurs. The first important special case is that P is equal to 1. How to understand it? That see, when P equals 1, right, this is L1 convergence, right, also called mean convergence. It means the expected absolute error tends to 0, right? The second important special case is P is equal to 2, right? This is L2 convergence or mean square convergence. It means the expected square error tends to 0. L2 convergence is especially common in quantitative finance because variances, standard error, and quadratic hedging criteria naturally involve your squared quantiles. Then we go to next part, which is the key implication, right? X sub n converges in L to the P to X implies that X sub n converges to probability to X. The associated error condition is given by this equation. The expected value of the absolute value of X sub n minus X raised to the power P tends to 0. Why is this stronger than convergence in probability? Because convergence in probability only controls how likely the large error is. L to the P, right? Convergence also controls the average size of the error. So if you look at a diagrammatic explanation, what is happening, the vertical axis is the expected pth power error. The horizontal axis is n, the approximation of sample size. The downward sloping curve approaches 0. It represents progressively smaller average error as the approximation becomes more refined. So in a numerical pricing model, please understand two methods may both converge in probability, but an L2 error bound provides more information about the mean square accuracy. Okay, that is what we need to keep in mind. And then we get into the next part, which is quant finance example for Euler-Maruma error stochastic differential equation numerical method. Basically, Euler-Maruma is a numerical method for approximating the solution of a stochastic differential equation. The true stochastic differential equation is given by this formula: dx sub t equals a of x sub t times dt plus b of x sub t times dw sub t, right? So x sub t is the state variable at time t, dx sub t is its infinitesimal change, a is the drift function, b is the diffusion or volatility function, dt is an infinitesimal time increment, w sub t is Brownian motion, dw sub t is the Brownian increment, right? The Euler-Maruma approximation is x sub t sub k plus 1 superscript n equals x sub t sub k superscript n plus a of x sub t sub k superscript n multiplied by delta t plus b of x sub t sub k superscript n multiplied by delta w sub k, right? Here the superscript n identifies the numerical approximation. The times t sub k from the simulation grid. Delta t is the time step length. Delta w sub k is the Brownian increment over step k. The current value is updated using 1/5 contribution and 1 random diffusion contribution, right? The strong error condition at the terminal time is this one, which is basically the expected value, the absolute value of x sub capital T minus x sub capital T superscript n raised to the power p tends to 0 and then tends to infinity, right? Equivalently, this is what we have. So x sub capital T superscript n converges in L to the p to x sub capital T. This says that the simulated terminal state approaches the true terminal stage in average path or average pth power error. Financial implications include simulating GBM equity prices, distance stochastic volatility, CIR, interest rate, part dependent option payoff, scenario-based Greek and risk measure. Strong convergence concerns the accuracy of simulated paths or state value. It should not be confused with weak convergence, which concern distributions or expected test function, right? Technical clarification here is that when we are trying to study it, right, please understand that Monte Carlo pricing uses simulated path. If strong error is small, right, simulated payoffs are accurate. Using numerical methods for GBM, Heston, CR, etc. LP convergence guarantees the approximation. Error vanishes in an average, right? Basically, it should be average sense, right? So that word you have to understand. Then we go to the next one, slide number 11. Basically, convergence and distribution. We're looking at weak convergence definition. The cumulative distribution function of a random variable y is given by this equation. F sub y of x equals the probability that y less than or equal to x. Convergence in distribution is defined by this equation. and f sub y of x equal the probability of y less than or equal to x, right? So again, when I look at this equation, f sub x sub n of x tends to f sub x of x at every continuity point of f sub x. The notation is this one. Basically, x sub n converges in distribution to x, only the probability laws need to approach one another. X sub n and x do not even have to be constructed on the same probability space. The restriction to continuity points is important because the distribution function may jump at values having positive probability. Convergence in distribution is weaker than convergence in probability because it says nothing about whether x sub n and x are close for the same outcome, right? So remember that point. Convergence distribution is the weakest common convergence notion. Distribution being closer as n increases. Only the law of x matters, not pathwise closeness. Then we get into the next part, which is convergence in distribution. We're looking at CDFs converge, shape of distribution stabilizes. So the slide basically repeats your x sub n converges in distribution to x. This means the CDF curve of x sub n approaches the CDF curve of x. It does not necessarily mean this equation, right? X sub n of omega tends to x of omega. The later is a pathwise statement and is much stronger. And then we have graphical explanation. The horizontal axis contains possible value of the random variable. The vertical axis is the CDF ranging from 0 to 1. The solid curve is the limiting CDF. The dash curve is the approximating CDF. The curve becomes closed as n grows. Okay. And institutional distributional convergence is enough for many limit theorems, such as the central limit theorem. It is not enough when the path accuracy is required, right? So why it is called weak convergence? Focus on the distribution behavior, ignore simple path accuracy, is enough for many limit theorems in probability, right? Then we get into the next slide. The key results in the convergence in distribution, your Donsko's invariance principle, random walk tends to Brownian motion basically. The increments again satisfy this equation. Basically, the probability that z sub k equals +1 equals the probability that z sub k equals -1, both are equal to 1/2. The scale process is this: w sub t superscript n equals 1 divided by the square root of n multiplied by the sum from k equals 1 to the floor of nt of z sub k, where t lies between 0 and 1 inclusive. The correct Donsker equation is given your W superscript n converges in distribution to W. This is not merely convergence of one terminal random variable. The entire random walk process converges in distribution to standard Brownian motion in an appropriate path space. The financial connection here is that Donsker theorem explains why a sequence of small independent up and down shock produce a Brownian limit. Discrete binomial price dynamics can converge to GBM. Continuous time stochastic calculus can model the limit of high frequency discrete price changes, right? And then we have technical clarification. The slide displays W superscript and the DW because the convergence arrow is missing. It should be read as kind of convergence and distribution as written above, right? So that is what is important, right? Financial meaning, Brownian motion is the core driver behind a continuous time price model. This results explain why Brownian motion is a valid continuous limit of discrete shocks. Using building intuition from binomial model leads to your Black-Scholes world. Then we go to your slide number 14, which is very theoretical in nature. Basically, implications between your convergence types, why different convergence notions matter. Fairly theoretical, we are looking at practical finance reason and strongest versus weakest. So different problems require different kinds of control. When you're looking at convergence concept, almost sure what it controls is that individual paths outside null set, typical financial use with pathways or pathwise theorems and long-run simulation stability. If a convergence concept is in probability, what it controls is probability of material error. Typical financial use case is consistency of estimator. If your convergence concept is L to this P, what it controls is average pH power error. Typical financial use is numerical SDE error and quadratic hedging. If your convergence concept is in distribution, what it controls is shape of the probability law. Typical financial use is your CLT, right? Central limit theorem, asymptotic risk, and discretize to continuous limits, right? So I'll again repeat, see, please understand, almost sure is for pathwise theorems and long-run simulation stability. Improbability is for consistency of estimators. L to the P is for numerical stochastic differential equation error and quadratic hedging. Your in distribution is for central limit theorem, asymptotic risk, and discretized to continuous limit, right? The strongest available result is not always necessary. For example, the confidence interval may only require a distribution limit. Accurate payoff simulation may require strong path convergence. Passing limit to an expectation may require additional tail control. Okay. Implication diagram here, strongest to weakest. The side states the following chain, right? X sub n converges almost surely to X implies X sub n converges in L to the P to X, which implies X sub n converges in probability to X, which implies X sub n converges in distribution to X, right? This chain is not correct in general because almost sure convergence does not automatically imply L to the P convergence. This universally valid almost sure chain is, right? And the basically idea is X sub n converges almost surely to X implies X sub n converges in probability to X, which implies X sub n converges in distribution to X, right? The valid L to the P chain is basically X, this part, right? This part from here to here. So X sub n converges in L to the P to the X implies X sub n converges in probability to X, which implies X sub n converges in distribution to X, and without additional tail or domination condition such as X sub n converges almost surely to X does not necessarily imply that X sub n converges in L to the P to X, right? So almost sure convergence and your L to the P convergence should therefore be viewed as two different strong branches, both imply convergence and probability. Additional condition, right? Additional condition such as domination by and your integrable random variable or suitable uniform integrability condition can connect the branches. Okay, so reverse condition generally do not hold. Remember that. Almost sure is strongest, distributional is weakest. Then we go into the next one, which is law of large numbers. Law of large numbers, most practical convergence result in finance, right? The slide assumes independent identically distributed observation with your equation, this one. Basically, the expected value of the absolute value of X sub n is less than infinity. This is the finite first moment condition. It ensures that the population mean is well defined. The sample mean is given by this equation. X bar sub n equals 1 divided by n multiplied by the sum from k equals 1 to n of X sub k. The sample mean estimates the population expectation as the sample size increases. Positive and negative sampling fluctuations tend to average out. Financial applications include averaging simulated option payoffs, estimating expected portfolio loss, calculating average returns or default rates, aggregating scenario-based exposure, right? So the law of large numbers explain convergence of the estimate. It does not describe the speed of the finite sample uncertainty. That role is primarily placed by the central limit theorem, right? That is what we have. X bar n is the estimator of expected X1. As n grows, randomness cancel out and averages become stable. Financial relevance is Monte Carlo option pricing based on averaging payoff. Risk estimation uses averaging similar pay loss. Law of large numbers, weak. Law of large numbers, convergence in probability, Monte Carlo code, right? So weak law of large numbers basically is given by this equation. What does it mean? Basically, X bar sub n convergence of probability to the expected value of X sub 1. So equivalently for every positive tolerance, right? We have this equation, the probability that the absolute value of X bar sub n minus the expected value of X sub 1 is greater than epsilon tends to 0. For similarity terminal payoff, the estimator is given as this equation. Basically, V hat sub 0 equals exponential raised to the power minus RT multiplied by 1 divided by n multiplied by the sum from k equals 1 to n of h sub k. Here h sub k is the terminal payoff in simulation k. The large sample approximation is given by this equation. V hat sub 0 is approximately equal to the power minus RT multiplied by the expected value under your QFH, right? The risk neutral measure is used because this is a pricing exercise, right? So I told you, right, for pricing exercises and hedging, we use neutral measure. A real world loss forecast would normally use the real world measure instead. The weak law of large numbers tell us the estimate becomes accurate in probability. It does not by itself provide a confidence interval or your error bar. Then we get into the next part, your strong law of large numbers, almost sure convergence, pathwise guarantee. When you look at strong law of large numbers, this x bar sub n converges almost surely to the expected value of x sub 1 for almost every infinite sequence simulation result. The successive sample average settles toward the mean expectation. The pathwise, this is given by your x bar sub n of omega tends to be the expected value of x sub 1. The convergence may fail for a null set of simulation sequences, but the probability of that acceptance set is 0. The strong law of large number is stronger than the weak law of large number because almost sure convergence implies convergence in probability. In Monte Carlo pricing, it gives the theoretical assurance that almost every indefinitely extended simulation run will eventually kind of stabilize around the corrected expected payoff. Okay, so for almost every outcome, omega, the sequence x sub n bar, omega converges. Failure happens only on a null set of probability 0. Why strong law of large number? Because weak law of large numbers, high probability closeness, strong law of large number, active convergence for almost all simple paths. If you run Monte Carlo with large n, the estimate becomes stable for almost every simulation outcome. Strong law of large number gives a deeper guarantee and supports a stronger theoretical results. Then we get into this part, your central limit theorem. Why average becomes kind of normal? Because please understand the assumptions are these. Basically, the expected value of x sub I equals mu and the variance of x sub I equals sigma squared, which is less than infinity. The variables are assumed to be IID, independent and identically distributed. This variance should also be positive for the standardized formula. The sample mean is given by this formula. X bar sub n equals 1 divided by n multiplied by the sum from I equals 1 to n of x sub I. The standardized central limit theorem is this. The square root of n multiplied by x bar sub n minus mu divided by sigma converges in distribution to a normal distribution with mean 0 and variance 1. The equivalent unstandardized form is this one. Basically, the square root of n multiplied by x bar sub n minus mu converges in distribution to a normal distribution with mean 0 and variance sigma squared. The central limit theorem does not say the original observation are normal. It says that the properly scaled estimation error become approximately normal for large sample. This provides the foundation for Monte Carlo standard error and your confidence intervals. Then we get into next part, which is graphical interpretation, finance connections of central limit theorem, Monte Carlo plus risk plus hedging. Why confidence central limit theorem matters in quant finance? Because confidence intervals of Monte Carlo estimates variance direction, control variance antithetic, hedging error distribution in rebalancing, or expected shortfall asymptotics for large portfolio, right? So the Monte Carlo estimator is given by this equation, mu hat sub n equals 1 divided by n multiplied by the sum from I equals 1 to n of x sub I. For large n, its approximation distribution is given by this equation. Mu hat sub n is approximately normally distributed with mean mu and variance sigma square divided by n. The standard error is given by this equation. The standard error of mu hat sub n equals sigma divided by square root of n. The standard error decreases only with the square root of the simulation count. Therefore, reducing the standard error by half normally requires approximately 4 times as many independent simulation. We have a graphical explanation here. The horizontal axis show possible estimated value. The vertical axis show probability density. The small sample curve is wider and lower. The large sample curve is narrower and taller. Both are centered near the same true mean. The narrowing reflects the variance decreasing with your sample size. If you look at finance use cases, please understand the confidence interval for Monte Carlo prices comparing variance reduction method, approximating portfolio loss distribution, analyzing your discretely rebalanced hedging errors, large portfolio approximation for war, expected shortfall. Okay. Then we get into your slide number 21, which is about uniform integrability. We're looking at preventing mass escaping to infinity. Okay, uniform integrability controls the tails of an entire family of your random variables. The definition which is given, right? Limit as k tends to infinity of the supermum over n of the expected value of the absolute value of x sub n multiplied by the indicator that the absolute value of x sub n is greater than k equals 0. So k is the tail threshold, the indicator equals 1 when the magnitude exceeds k and 0 otherwise. Multiplicative or multiplication by the indicator keeps only your tail observation. The expectation measures their contribution. The supermum over n takes the largest tail contribution across the whole family. Uniformity means a single sufficiently large threshold controls every member of the family. And uniform integrability prevents a sequence from placing similar probabilities on increasingly extreme outcomes while still retaining a large expected contribution. In finance, this matters for heavy tail payoff and losses, martingale convergence, stopping your time arguments, interchanging expectation and limits, numerical payoff convergence, etc. Okay, so this is what we have. Please understand, uniform integrability says tail contribution to expectation can be made in small uniformly in n, where uniform integrability PS is martingales and stopping times, emergence of payoffs in stochastic models, limit switching in expected values. Okay. And intuition is also given here. Prevents expectation from being dominated by rare extreme events and ensure tails do not contribute too much mass and n changes. Then we go to your slide number 22. We are continuing with why uniform integrability matters, linking your convergence and your expectations. So main role of uniform integrability bridge convergence in probability with convergence of expectation. Key result is this. Basically, x sub n converges in probability to x and the family x, right? Sub n is uniformly integrable, implies that the expected value of x sub n tends to the expected value of x. Convergence in probability alone does not guarantee convergence of expectation. Rare but increasingly extreme values can disappear in probability while still affecting the mean. The tail condition illustrated in the diagram is given by this is a difficult looking formula, but it is the supermum over n of the expected value of the absolute value of x sub n multiplied by the indicator that the absolute value of x sub n is greater than k tends to 0 as k tends to infinity, right? So diagrammatic explanation is, if you look at the full rectangle basically, in fact, the total rectangle represents total expected contribution. The narrow right-hand region represents the extreme tail. Okay, that is what we have. And uniform integrability shows that the tail region contributes very little uniformly across n. When the tail is controlled, convergence of the random variable can be transferred to their expectation. In derivative pricing, this distinction is very, very crucial because distributional or probabilistic convergence of simulated underlying prices does not automatically imply convergence of expected unbounded payoff. Tail control supplies the missing step. Okay, that is what we need to understand. Okay, so this is what I have written above also. Why this matter in quant finance? Because martingale convergence theorem often require uniform integrability. Expected payoff convergence in numerical stochastic differential equation schemes. Stable convergence of your Monte Carlo estimator for payoff with your MQF. Okay. Then we go into next part, convergence concept in quant finance. Why convergence in everywhere in quant finance, right? Basic idea is that quant finance usually limit constantly discrete models approximating continuous time markets, numerical method approximating stochastic differential equation solution, sample moments approximating population moments, hedging strategies approximating continuous hedging, Main idea is different convergence notions appear depending on what we need. Convergence in distribution weak, convergence in probability, your LP convergence, strong error model, strong error control, almost sure convergence, pathwise, finite takeaways, convergence guarantee that simplified models and simulation produce reliable results. Basic idea is convergence is everywhere in your quant finance, right? And quantitative finance constantly moves between approximations and your limiting objects. Discrete time to continuous time. Finite simulation sample to exact expectations. Estimating moments to population moments. Numerical stochastic differential paths to exact paths. Discrete hedges to continuous time hedges. The required convergence concept depends on the question. Distributional convergence suitable when only the limiting law kind of matters. Convergence is in probability is suitable for consistency. L to the P. Convergence is suitable when average error magnitude matters. Almost sure convergence is suitable when pathwise behavior matters. Uniform integrability is needed when expectation and tail must remain stable. So convergence is therefore the mathematical justification for using your tractable approximation in pricing and the risk management. Okay. Then we get into the next part, which is about convergence concept in quant finance, but we are talking about your discrete time models converging to your stochastic differential equation model. Again, a classical result in derivative pricing, binomial model converges to your Black-Scholes model. Core mechanism is log price in binomial model behave like a scale sum of increments. By central limit theorem, invariance principle, these converges in distribution. Convergence statement is this. Basically, what happens is that the logarithm of S sub t, superscript n converges in distribution to the logarithm of S sub t, which implies that S sub t superscript in convergence in distribution of S sub t, right? So the second implication follows because the exponential function is continuous. This is an application of the continuous mapping theorem and the time step condition we have, right? At delta t tends to 0. As the time step shrinks, the number of binomial replacing or rebalancing dates increases. The discrete stock model approaches GBM. Metric Brownian Motion, the CRR option price approach Black-Scholes price under your appropriate assumptions, right? So in financial meaning, discrete up-down models become continuous GBM as time step delta t tends to 0. Explain why Black-Scholes continuous time limit of binomial pricing. Practical use, I told you, explain CRR binomial accuracy improving in most step and support convergence of discrete option price to your Black-Scholes price, right? So convergence in distribution of the underlying terminal price does not by itself guarantee convergence of every expected option payoff or bundled or bounded continuous payoff. It is usually sufficient for unbounded payoffs. Additional moment or uniform integrity control may be kind of required. Okay. Then we get into next part, which is convergence concept in quant finance, convergence in our numerical methods for stochastic differential equations. In practice, we simulate the continuous time models numerically. For example, we have Euler-Maruyama scheme, which is given by this equation: x sub t sub k plus 1 superscript n equals x sub t sub k superscript n plus a of x sub t sub k superscript n times delta t plus b of x sub t sub k superscript n times delta w sub k. The desired terminal strong error result is given by this equation. The expected value, the absolute value of x sub capital T minus x sub capital T superscript n raised to power p tends to 0. The numerical solution should approach the exact solution as the grid becomes kind of finer. A smaller time step generally provides your lower discretization bias, more accurate path-dependent payoff, more reliable simulation based Greeks, higher computational costs. The strong convergence is kind of important when the payoff depends sensitively on the path. Like weak convergence may be enough when only the expectation of a sufficiently regular terminal payoff is required. Right? So in financial relevance, Monte Carlo pricing option under GBM, Metric Brownian Motion, Heston model, Cox-Singleton-Ross model, simulation-based Greeks, and risk metrics depend on the accurate stochastic differential equation path. Smaller delta t gives better approximation but higher computational cost. Okay, so what convergence mean is that we want numerical solution to approach the true solution as step size decreases. Fine. Then we get into your slide number 26, convergence concept in quant finance. We're looking at convergence of empirical methods, data to your true parameters. Let the observed returns of let the observed returns be R sub 1 through R sub n, right, which is given here. The sample mean is given here. R bar sub n equals 1 divided by n multiplied by the sum from I equals 1 to n of R sub I. Under your law of large numbers, we get this R bar sub n tends to the expected value of R at n tends to infinity. The slide sample variance estimator is given by this x s sub n squared equals 1 divided by n minus 1 multiplied by the sum from I equals 1 to n of R sub I minus R bar sub n all squared. Under your standard condition, it is given as this s sub n squared tends to the variance of R. For IID returns with a finite second moment, these convergences can be established strongly. If you're looking at financial interpretation, the sample mean estimates your expected return, the sample variance estimate your return variance, volatility, the square root of variance. So the slides phrase volatility estimator is slightly informal here, but historical estimator generally concerns the real world return distribution, not the risk neutral distribution, right? Financial meaning is expected return and volatility are estimated from historical data. Convergence from justifies long data windows for stable parameter estimates, right? Longer data window increases your sample size, but may introduce stale data or regime changes. Convergence theory assumes a stable data generating process. It does not eliminate model instability. Then we have convergence concept in quant finance, convergence of hedging errors, trading frequency. Basically, discrete hedging uses rebalancing time, your T0, T1, Tn. How to pronounce it is that T sub 0, T1, Tn. As the hedging interval decreases, as your delta T decreases, discrete hedging approaches continuous hedging. And delta T tends to 0, which implies the discrete hedging approaches continuous hedging. Slide gives you a distributional limit, which is hedging errors sub n convergence distribution to a limit distribution. This type of limit helps quantify your residual hedging risk, construct your confidence interval, estimate capital for your option books. More frequent hedging normally reduces your discretization error, but increases your transaction cost, market impact, your operational burden, your exposure to bid-ask spread, which you need to understand, right? So please keep in mind that mismatch between two continuous hedge and discrete hedge create error. Financial meaning is more frequent hedging reduces error, but increased transaction costs. Limit distribution helps quantify residual risk in real hedging. Using risk estimation of options portfolio, practical takeaways, hedging is never perfect in reality. Convergence helps us measure the remaining risk. Okay, so that is what we can do. Then we go into your practice questions. We are theory part of the chapter is over. The question is, the given sequence is x sub n equals 1 divided by n. Okay. The required conclusion are x sub n converges almost surely to 0. And x sub n converges in probability to 0. So the sequence is deterministic, and basically we have what? Limit n tends to infinity 1 by n equal to 0. The limit as n tends to infinity of 1 divided by n equals 0. Therefore, it converges for every outcome which is stronger than merely almost everywhere convergence. For any positive epsilon, right? For any positive epsilon, your the probability that the absolute value of x sub n is greater than epsilon equals the probability that 1 divided by n is greater than epsilon, and this tends to 0. Indeed, once n is sufficiently large, the inequality becomes false and the probability is exactly 0. There are no multiple choice options on the slide here. So the common incorrect answer would be to claim that determinism prevents almost sure convergence. In fact, determinism or deterministic convergence automatically gives convergence for every outcome. Okay, so that is what we are looking for. The detailed solution is given ahead also, but I've explained you the logic. Then we have your question number 2. the random variable is given here. X sub n equals the indicator of the event that x is greater than 0 or less than 1 divided by it or 1 divided by n. The indicator equals 1. The next lies in the shrinking interval and 0 otherwise, right? So the required result is xn 0, right? X sub n converges probability to 0 for a tolerance between 0 and 1, right? For between 0 and 1, right? Epsilon is greater than 0 and less than 1 because x sub n only takes 0 or 1. So we get the probability that the absolute value of x sub n is greater than epsilon equals the probability that x n equals 1, which equals the probability that x is greater than 0 and less than 1 divided by n, and this tends to 0, right? The interval is into the empty set because 0 itself is excluded, therefore the probability tends to 0. For a tolerance of at least 1, your epsilon is greater than or equal to 1, therefore probabilities of your epsilon greater than or equal to 1 implies that the probability that the absolute value of x sub n is greater than epsilon equals 0. So the definition holds for every positive epsilon. A stronger conclusion is also true for every fixed outcome. The indicator is eventually 0, so the sequence actually converges pointwise everywhere, and hence almost surely there are no other options given here. A common mistake is to assume that x must have a continuous distribution. No continuity assumption in here. Then we go to question number 3. Again, we have been given an equation W sub t, right? Divided by t converges in L, right? L2 to 0 as t tends to infinity. For standard Brownian motion, where this is the equation, the expected value of W sub t squared equals t. To prove L2 convergence, calculate the mean squared error, which is expected value of W sub t divided by t all squared equals 1 divided by t squared multiplied by the expected value of W sub t squared, which equals 1 divided by t squared multiplied by t, which equals 1 divided by t, and this tends to 0. Therefore, the correct answer is WT W sub t divided by t converges in L2 to 0, right? L2 convergence also implies convergence in probability. There are again no options given here. The common incorrect approach is to consider only the mean. The mean is 0 for every t, but a 0 mean alone does not prove convergence. The second moment must also shrink, right? That is very, very important. Okay. Then we have the detailed solutions. This is what I was talking about, even though I have already written, but you can read this solution here also. The deterministic limit is given by this. The limit present tends to infinity of x sub n equals 0, which implies x sub n converges almost surely to 0. For convergence in probability, we have this equation. The probability that the absolute value of x sub n is greater than epsilon equals the probability that 1 divided by n is greater than epsilon, and this tends to 0. The combined answer is this one. X sub n converges almost surely to 0. The x sub n converges in probability to 0, right? More precisely, for any fixed positive epsilon, the probability becomes exactly 0 once n exceeds 1 divided by epsilon. Then we go to the next part. Next solution we have for a tolerance in the open interval from 0 to 1. I've already written the solution there, right? But this is a little detailed, right? For a epsilon belonging to the open interval from 0 to 1, then we have this equation. The probability that the absolute value of x sub n is greater than epsilon equals the probability that x sub n equals 1, which equals the probability that x is greater than 0 and less than 1 divided by n. It then grows the interval decrease to the empty set. So we get this equation, right? Basically, this equation tends to 0, right? Probability. Probability that x is greater than 0 and less than 1 divided by n tends to 0, right? Which is this x sub n converges probability to 0. The official solution, which is given here, proves the requested convergence in probability, right? We saw in the previous slide, in slide number 29, the result can be strengthened to almost sure convergence because the indicator is eventually 0 for every fixed outcome. Okay, last but not the least, we go to solution of the third question, right? Again, the equation is given here, the expected value of W sub t divided by t all squared equals 1 divided by t squared multiplied with the expected value of W sub t squared, which equals 1 divided by t squared multiplied W, which equals 1 divided by t, and this tends to 0, right? This proves this equation, W sub t divided by t convergence in L2 to 0. The implication shown here is W sub t divided by t convergence in L2 to 0, which implies that W sub t divided by t convergence in probability to 0. The official calculation is the squared L2 norm. The L2 norm itself is the square root of that quantity, and hence it also tends to 0, right? So overall, the joint picture here is, since we are at the end of the chapter now, right, and we have done practice question also, theory also, please understand the lesson is basically connecting your 5 major ideas, right? The first one is almost sure convergence controls what happens along almost every individual path. Convergence in probability controls the probability of a material approximation error. L to the P convergence controls the average size of that error. Convergence in distribution controls only the limiting probability law, and uniform integrability controls extreme tails and allows convergence to pass through expectation. Okay. The correct general structure is that both almost sure convergence and L to the P convergence imply convergence in probability, which then implies convergence in distribution. Almost sure and L to the P convergence are not generally order related to each other. These ideas justify the core approximation used throughout quantitative finance. Monte Carlo pricing through the law of large numbers and central limit theorem, binomial convergence to Black-Scholes through invariance principles, numerical stochastic differential equation simulation through strong or weak convergence, parameter estimation through empirical movement convergence, and risk control through tail conditions such as uniform integrability, UI. Okay. So again, a tough topic, not very long as the previous one, lesson number 1.2, that was very long. Not that long, but yes, it's a tough one. Go back and revise it, guys. At least do it twice or thrice, right? Stochastic calculus is not easy. Not easy at all, right? So you have to pay a lot of attention. The biggest challenge is not only to understand how these concepts work, but also to understand how they fit in the world of your quantitative finance, whether it is risk management, portfolio management, any other kind of derivative pricing, hedging, etc. Right? So you have to be very, very thorough. You have to understand the implications. You have to understand the limitation. You have to understand the assumption. You have to understand the formula as it is, right? Correctly in a correct format, right? So go back, revise it, do a deep dive, at least do it thrice. You'll be fine, right? That's it, guys. That's it for this lecture. I'll see you in the next lecture, and then we'll proceed ahead. Okay. All right, guys. Thank you.